Let's see. All right. So I kind of want this to be a discussion, but before we get to the discussion, I think I need to do a little scaffolding of the discussion. I do work in geo, but mostly from the perspective of small little creatures and their omics. Usually, as a chemical engineer, what I'm trying to do is steal their features and use them in an industrial setting, but sometimes we look at things like carbon and nitrogen cycles. So reproducibility and open science is something that I'm passionate about, along with hearing the sound of my own voice, but I will try to keep that to a minimum so that we can talk. But I think I need to start with giving us some vocabulary that we can kind of converge on. So one of the primary facets of reproducibility, and I think the basic one that we should all keep in mind, is technical reproducibility. So with the same data and the same code, when I run the tool again, I should get the same result, right? So we don't want our code to be stochastic. We want it to be reproducible. In that sense, if you go up one level, how reproducible is the algorithm, right? So if I publish my methods and you get my data and re-implement my algorithm, is it reproducible to whatever degree you consider your epsilon, whatever the convergence criteria are. So this, in a way, reflects how well did you describe your methods for other people, right? So the last one is then, can the study be reproduced? So in principle, there is an equivalent set of data that you have collected, and there is a re-implementation of the algorithm. If you did the study over again, could it be replicated, right? So I often think in these three levels, and the first one can be the hardest one to get right, and we'll talk about some basic strategies for dealing with that. The other ones are a lot about how you communicate your results and your methods, and then how you do your study design, right? If your study is underpowered, you may get one result one time and not the second time, and then it's not replicable, right? But you may have described it to folks great. Okay. So there are another set of terms that I don't think I'm going to spend a ton of time on that get at actually attaching labels to all the different aspects of this, and I encourage you to go look at this. This is the ICERM report. Stoddard's the first author from 2015, and they go through 5 different terms. Whether your research is reviewable, so this is like, how well did you write your methods? Is it replicable? Like, did you make the things available for people to reproduce your research? Is it confirmable? So are the fundamental ideas that you are going after, are those main conclusions, can they be reproduced independently without your involvement at all? And then, is it auditable? So how good are your lab notebooks, right? And then finally, at the top level, is it reproducible? So if you combine all of these other things, that gives you reproducible research. So I think it's great to go in and look at this terminology, and it's important, and I want you to solidify it in your mind, but I think for the purposes of our discussion, that's enough of an overview. Any questions on that? Okay. I give a lot of these talks, and this is probably my favorite part, but it's also the most depressing part, which probably says something about my personality. But I kind of want to go through a few high-impact replication failures out there. I talked about working with tiny little organisms and their omics, which also means I get to do stuff with NIH. So some of this is from the human health perspective, and let's be honest, that's where all the money is anyway. So in 2011, Bayer Pharmaceuticals looked at 67 important papers to their business model. So if you know anything about Bayer, they do a lot of work in oncology, women's health, and cardiovascular medicine. So they looked at 67 important papers in these fields and tried to reproduce them. Anybody want to guess what percentage were reproducible? 10? Anybody higher to 2%? Okay, well, you guys weren't that bad far off. It was 21%, which is kind of depressing when you think about it. 2012, Amgen did something similar, looking at 53 studies in cancer. Anybody want to guess? 20. You're going the other direction. It was 11, right? So we're setting the stage here for something that, if you were looking at Nature last year, they called the reproducibility crisis in science. Ioannidis, who's quite well known for doing these studies, went and picked out 18 tables and figures from papers published in Nature Genetics using a very specific technology. So now we're narrowing down what we're trying to reproduce, just tables and figures, not conclusions, and just microarray data, which is a specific technology that's used in transcriptomics. And what they found was interesting. I mean, you know, over here on this, where's my mouse? Over here on this side, you know, this green side, you might think that that's good, right? Because that's the could be reproduced. But if we drill down into what those labels are, it's a bit telling. So this chunk here, wait, where's my mouse? This chunk here, which is perhaps the most positive assessment, was can reproduce in principle. Not can reproduce wholly, but can reproduce in principle. So the best that they were able to do was to reproduce some number of these in principle. Then this other group here is reproduce with discrepancies, reproduce from process data with discrepancies. So microarrays goes through multiple processing steps, and they couldn't start with the raw data and reproduce them, but if they start with some of the process data, they could get there, right? And then can reproduce partially with some discrepancies. So this whole group over here, which is supposed to be the plus side, the good part, is all in principle or with discrepancies, right? So that's a little bit frustrating. And then if you look over here, perhaps what's more interesting for us to talk about is the cannot reproduce group, right? The more than half that could not be reproduced. And if you look at these four possible reasons, there's one that's not all that helpful, which is different result, right? We don't really know what the underlying cause of the failure to reproduce there was, right? But a good chunk, probably about half of the ones that couldn't be reproduced because they weren't able to obtain the data. Right? So this is the open science side of reproducibility. You have to be able to get the data. Another aspect of the open science side of reproducibility is the software wasn't available, right? So great, the data were available, but I couldn't actually get the code that was used. And that's why I hope you all are working with GitHub. And then this other chunk here, the method's unclear. And I think this is a little bit harder for us to nail down in terms of specific tools that you can use, because this is about how well you write your method sections, or how good of a communicator you are. And so I guess one of the things I want to suggest to you is that computational reproducibility isn't just about code or data, that there is a human component here, which is about your level and ability to communicate. Okay, so in this setting, what are the repercussions to these irreproducible results in medicine? Well, for biotech companies, it's billions of dollars of money that's wasted. So if you're not familiar, it takes 10 to 15 years to get a drug to market, and it's anywhere between $1 to $1.5 billion to do that. So that's a tremendous amount of money that just gets wasted on bad science, right? Similarly, the government invested in this research. Almost certainly it was the US government that invested in a lot of this research, which means that was wasted dollars, right? That was wasted taxpayer dollars and wasted funding dollars. And I think we're all painfully aware of how slim funding is right now, right? And then I had a really interesting, when I did this lecture for some folks in medicine, they had this order reversed. So for them, it was the people, right? When their biggest concern was not so much that biotech companies lost some money, or even that government grant money wasn't perfectly used. It was that there were potentially patients that died, right? Because there was a drug that could have been brought to market had the science been done correctly, but they weren't able to get that drug. Or, flip that around, that they were treated with a drug that actually wasn't efficacious because the study wasn't done properly. All right, so I'm going to switch gears from medicine to economics, because if you thought that was a big deal, I think many people feel that this particular economic instance was even bigger. So if we put on our Wayback hats and go back to the unpleasant times of 2010, if you look at the GDP, US GDP, over the years, you notice that the GDP fell, and that's really uncommon in US history. And right here we were sort of in the depths of the Great Recession, right? Similarly, if you look at the world GDP, it was on the decline, which is also relatively unheard of in modern times. And breaking this world GDP out, you can see that a big chunk of this was, BRICS, right? But then right over here, these rich countries, this had a substantial decline, and it tracks in a very pronounced way with this global GDP decline, right? So 2010, and there's this big tracking down. And if you think about which countries can borrow, it's the rich countries and maybe the BRICS, right? So they have the financial power, even in recession, that they can borrow against their national debt. So 2010, Reinhart and Rogoff, two economics professors from Harvard, published a paper called Growth in the Time of Debt. Anybody aware of this paper? It actually made it into presidential elections. It was brought up in debates and stuff. And essentially their conclusion was that high debt to GDP ratios, 90% and above, are associated with notably lower growth outcomes, right? So if you're trying to grow your way out of the recession, you don't borrow, right? And this led austerity, right? I think there was a time when many of us were tired of hearing austerity, right? So this was a premier argument that austerity, austerity, austerity. Don't borrow, just cut your budget, cut your budget. And they actually gave a number to this. They said that your economy will shrink if you're over 90% debt to GDP by a small percentage, but it's shrinking, right? And the final stamp, the thing that the IMF and all these organizations took away, the EU, was that countries don't grow their way out of debts that they incur in recessions. So it was super widely cited, as I mentioned. Everybody grabbed onto this. It was the basis for austerity all over the world, and it made its way into the presidential election. So great class that they have at UMass Amherst, where their first-year economic graduate students have to reproduce an existing economic study out there. If you're looking for spinning up a course in your program, like these reproducible courses are really fun to do. And in this class, he tried to reproduce their study and he couldn't. This is Thomas Herndon. And he asked Reinhart and Rogoff for the code, and my understanding is that they were very reluctant to share, and that it took a fair amount of time to get it from them. But when they finally got it from them, it wasn't code; it was an Excel spreadsheet, right? So that may raise some red flags right there for you folks who spent a week writing code. And then digging through it, he actually found multiple errors. So this is a quote there that he found coding errors, right? Selective exclusion of data and unconventional weighting, so statistical errors in there too. And all of this led to a serious inaccuracy in the results, and in fact a modified conclusion that if you have a high debt to GDP ratio, say you're trying to borrow your way out of a recession, that you can have real GDP growth in 2.2%, right? That you can have a positive growth. So in fact, the actual conclusion that austerity is the right way to go was wrong, at least based on this study, and that maybe we should have been letting Greece borrow their way out of their recession. And again, coming back to this, it's the rich countries that can borrow, right? It was the countries that had this big decline in their real GDP down here that could have actually maybe kept their economies at least stagnant, or maybe even grown at a 2.2%. So if we think about the global impact of that, I mean, it's tremendous, right? The number of people who were touched by the austerity sort of party line, if you will, is everybody on the planet in some sense, right? So in Nature, in 2016, there was this whole study about, is there a reproducibility crisis in science? And if you look at this, again, 10% were either weren't sure or thought there wasn't a crisis, but all the rest of science felt that there was. And I should add that this study of maybe 1,500 or so researchers included folks from all over the spectrum. So it wasn't just medicine or health. It was, astronomy, physics, geospatial sciences, I'm sure. So why do we care? And I love this quote from Karl Popper, where non-reproducible single occurrences are of no significance to science, right? If you can't reproduce it, then it doesn't lend anything to science, and it doesn't help science grow. I think right now, one of the things that we should all be particularly cognizant is that there is perhaps a general decline in the faith of science and the scientific method, and that has impact on the availability of funding, right? So if the general populace doesn't think that science is useful or valuable because it's not reproducible, then they're not going to advocate to their representatives in Congress to keep approving bigger and bigger budgets. So if you value your own academic future or other type of future, I think it's important that we convey a message of strong reproducibility to the broader community. Okay. So from a less radical and incendiary way, why we want to avoid it is, of course, this is the basis of science, right? So if we want to achieve scientific validity and integrity, then it has to be reproducible, and we have to be able to reproduce published results, and in fact verify published results. We have to provide evidence so that we can evaluate the reliability of a scientific claim, right? So one of my big gripes about Science and Nature papers is the methods section is buried in the supplementary material, and that's critical to know if they actually did the experiments right? This comes back to that methods and communication. And then, science builds by scaffolding on top of existing research, right? So if we have a whole bunch of inaccurate, irreproducible data, and we are trying to do the next building on top of that, the set of experiments to build on top of that, then that's just wasted time. That's graduate students who give up and frustrated and leave science, right? And then, of course, if your science is reproducible and reliable and people believe it, the impact for you is that they cite it, right? They use your software, and that goes into your promotion and tenure package, and then you get promoted and you get tenure, right? And then, this is sort of a little bit of like, eat your vegetables because it's good, but to promote data and code as a first-class research project, right? And this also is about you getting promoted. So right now, there is this culture of publication, 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 but if we as a community raise data and code to products that we expect to see on a CV and value them just as much as publications, then we contribute towards that culture. Okay. Then there's one final reason that if you're an academic researcher, should really care about this, and particularly if you do care about your publication count, and that's that, I hate to tell you, but retractions actually don't contribute to your citation count. They may contribute to their publication count, but not to your citation, right? Because nobody cites a retraction. Okay. So one of the core reasons that this is happening that I think that we're not going to talk about, I don't think today, unless you really want to, is that there's a relatively poor working knowledge of statistics, right? So, we're great at training bench scientists or experimental observers on those methods, but sometimes we neglect the statistics education. So the experimental design is underpowered, or the incorrect statistical test is used, or even the statistical test is not interpreted correctly. So, if you feel like you haven't taken a I think you would know if you haven't taken a statistics class in the last 3 to 5 years. But if you feel like your statistics are weak, then I encourage you to look at ways to improve your understanding of statistics. And statisticians as a group are generally nice people, and so maybe make friends with one. Good news is I had Sir Philip Campbell on campus he's the editor-in-chief of Nature, and we had a discussion around what Nature is doing to this, and they get it. They understand that there are problems with the statistical methods that are being used in their journals, and so they're getting better at recognizing these, but they're requiring statistical reviews of their manuscripts independent of the methodological reviews. So that's good, because the journals get this. All right, so let's turn now to things that you can do, and I think you're doing many of these. Use version control, and I don't mean like casually use version control. I mean it like you're an observant version control religious person. It's your detailed record of code development. I'm sure somebody already gave you this spiel, but I'll do it again because it's that important. It's your record of your code development. It will help you track and find and fix bugs. GitHub in particular has that issues thing, and if you haven't played around with it, it's a lot of fun, especially when you assign a bug to somebody else and blame it on them. And then it treats code like you would treat any research that you do in the lab. You have a lab notebook, that's part of your research, right? Just like version control should be part of your research. Write tests. Who writes unit tests? That's a resounding yes over there, by the way. Who writes good unit tests? You know, I probably should put my hand down. You write good unit tests?
Who doesn't know what a unit test means?
Who doesn't know what a unit test means? Okay, so if you think about your code and you break it down, let's say, into functions, right? So you're functionalizing your code. You're taking elements that you use repeatedly over and over again, and that's when you should use a function. Then you can write a test that will put in some controlled data, let's say, and test that the output of that function is as you predict, right? So you put in X, you get out Y, and that's what you expect. And then every time you add something to your code, or you change your code, or you modify that function, you can run that test again and make sure stuff didn't break. So there's this idea of regression testing, right? That as you move forward with your code, you don't actually break something. And so unit tests are a really important part of academic and science programming because they're your check on yourself, right? When you're trying to get that change done for the publication or for that grant proposal, this will help you check to make sure you didn't break something else.
I'm doing some image analysis and I've got just a image.
Yeah.
But at every line of code that I write, I'm running it again to see if so that would be it.
That's great. So yes, so that's the start of a unit test. What I would do is formalize that, and you can look at things like PyTest. I've got this up here. There are formalized structures that will help you run these unit tests automatically. And if you want to get really sophisticated, this is another reason to use version control, specifically GitHub. If you want to get really sophisticated, you can tell GitHub that when you submit new code, that it needs to go and run your unit tests again. Right? So you don't even have to, you can be super lazy and still get the benefit of unit tests. And I don't know about you, but I'm all into being lazy. Yes?
So one thing I've struggled with unit tests is usually in science you don't know the results of your analysis.
Yeah, that's a great point. So it's difficult to know what the result should be, right? In that case, it's good to think about how you can create a defined input where you can have an expected output. And there are times when that is an extremely difficult thing to do. There are times when it's pretty easy, like producing a correlation matrix from a pandas data frame. You can put in, it's not hard to imagine what data you could put in so that you get -1, 1, 0.5, right? Those kinds of things. But it can be a little bit more difficult, particularly when you're doing exploratory analysis. It can be a little bit difficult. In that case, one of the things that can save you is doing code reviews. Who knows what code reviews are? Okay, so code reviews are, you have to be friendly, but it's a time for you to look at somebody else's code and for somebody else to look at your code and help you find instances where your code could be improved. So we do this in my research group once a week, and the typical things that we comment on, or you named these variables after the 7 dwarves. What are they actually supposed to be for, right? So good variable names, good function names, but also structure of your code. Like, why are you doing this step before you do that step? Or, hey, you're doing this piece over and over again, maybe you should functionalize that. So code reviews are a way to have a sanity check, basically, on your work. And a lot of times, when you're doing complex algorithms, there's an opportunity for somebody else to find them. The important thing when you're receiving a code review is to remember that it's a loving, caring environment, and you want help. And then on the flip side, when you're doing a code review for somebody, I always joke, this is a joke in my group, but the compliment sandwiches taste really good, right? Like, I really like how you structured this. Maybe you should change that, and great variable names, that kind of stuff. So great, thank you so much. See, this is what I love about the discussion, is we get onto things that I hadn't meant to talk about. Right, so again, doing a unit test is example data, ideally small data so that your unit test doesn't take a year to run, with easily identified expected outcomes. Okay, I would say that when I asked that question about who writes good unit tests, I don't think any of us raised our hand in the room. And I will say that you get good at writing unit tests by doing them over and over and over again and recognizing what's testable and what's not. We had the comment about images, and I know that there's a lot of image analysis in the room. Thank goodness I don't have to do image analysis in my work. But writing unit tests for image analysis is actually quite challenging because you know, small changes in like registration of an image, or if you're producing an image, right? So you're taking an image and then producing another image from it. Those can be somewhat difficult things to unit test, and there's a body of literature actually in a bunch of Python tools around writing image unit tests. All right. Last year, I gave this talk at Geohackweek, and this was an actual comment, and this is why you need to be religious about using version control. My code was working yesterday, but today, and then they got a really unhappy look on their face, I didn't commit the script, and now it's not working anymore, right? So that's one of the, if you take nothing away from this, that's the one reason you should be using version control. There's a whole bunch of other ones, but that's the one that you want to save yourself from. Another one that I think doesn't get enough love is documentation. So I kind of split that out into overall documentation. Again, this comes back to how you communicate. What is your code supposed to be doing? What are the requirements for your code to work correctly? This is great stuff to put in your readme.md and your GitHub repo, right? Allison Smith over here, wave your hand, Allison, is probably my poster child for the best readme.md in a GitHub repo. And it contains everything you need to know to run her code, how to cite it. That's a good one to put in your readme.md. All the dependencies. I think she even tells people how to use the command line. Like, it's awesome. All right, then in your code, how you comment your code is important. You should accurately be describing what your code does, right? I like to think, I notice everybody's using Python notebooks. That's great, because it sort of encourages you to put lengthy comments in your code. But one of the things that's really important to remember is when you change your code, you need to change the comment. So I have that there, and I really truly believe that if a comment is inaccurate, it's the same as a bug, because as a reader of your code, I don't know whether the comment's wrong or the code's wrong, but one of them is, and that means it's a bug, right? So as you update your code, you need to update your comments, and vice versa. And then, you know, conveying to users now, not people that would be reading their code, what they should expect, how to properly use the tool. This is what I was talking about earlier, and then all the dependencies that are required to actually run your code. One thing I'll add here is that if you have an existing team and you're working on a project, and you bring in a new member, so you get that fresh graduate student or that undergrad or even that new postdoc or whatever, one of the great things to have them do is update, to survey, update, and then improve the documentation. And this is because it requires them to go through everything, right? They have to install the tool and run it and make sure that all those dependencies are met, right? And then they have to go through and make sure that the test data work. And they have to look at the functions to see if the comments are making sense. So bringing new people in by having them refresh the documentation is a really great way to familiarize them before you actually give them the keys to start writing code. Reproducible computing environments. So the computing environment matters, and time evolves. This is probably like my third or fourth Apple laptop I've had in the last 10 years, and I don't think a lot of the code, or even like Microsoft Word that I had on the first, would run on this one, right? So as computing environments evolve, as we get new computers, or there's new versions of Linux out there or whatever, underlying things start to change, like system libraries change, how things interact with network devices, or even image capture devices, or things like that. Those evolve, right? So if you wrote your code against a particular set of libraries, you're not guaranteed when that next version of the operating system comes out that that's going to behave exactly the same way. So creating stable environments are part of being able to reproduce a previous result. Even if your lab has moved on, having a way to capture a previous environment is important, because when that colleague 5 years later says, I would like to reproduce your work, and you can't because you don't have that computing environment anymore, that's part of being not reproducible, right? Math libraries change. Another thing that I think not all of us are acutely aware of is that the square root of 4 is 2, right? But to a computer, it could easily be 1.99999 or 2.01, right? It's not guaranteed to be an integer number 2. And if you're making the assumption that you're going to compare two floating point numbers, that is something that could have a decimal point, and it's going to be exactly some value, you're probably not going to be right. So there are things, does anybody remember, there's a Python thing that allows you to compare two floating point numbers, and it's like almost equals or something like that. So that's a handy thing to use, and you can set what the epsilon is of two numbers being almost equal. But it's important to recognize that. And so in one computing environment, again, the square root of 4 might be 2.01, and another it might be 1.999. And if you're making an assumption either way, you're violating kind of the underlying rules about how computers work. And then, of course, cataloging your work. So what are the operating system dependencies? What are the Python library dependencies? Are there any external dependencies? I don't know what GEE is. I don't remember when I wrote this. But wouldn't it be nice to know what version it was? OK. It's probably something Geo, you know. One of the great ways to do this is Docker. Did you guys do a Docker thing here? You did not do a Docker thing here. They did a Docker thing last year. So if you're not familiar, Docker is a way to create a static image of an operating system, and specifically usually Linux, that keeps system libraries, that keeps math libraries, that keeps whatever dependencies you install with it in perpetuity forever, right? So if you do all of your work in things like Docker images or in AWS machine images, who's familiar with AWS? Right? So this allows you, you can actually take a Docker image and run it in AWS, but you can create an image of a machine that will live forever independent of any specific hardware or any specific laptop or whatever. So these are a great way to create environments that you've basically said, save the state, right? You can even get DOIs for Docker images, which is really cool. That way you can say to somebody, you want to see my environment that I ran this in? Here's the DOI for it, and then it can go and reference a Docker image. And then, of course, data. So if I can't get your data, I almost certainly can't reproduce your study precisely. So open data is a super important thing. I keep telling you, I do omics stuff, and I'm so lucky because the National Library of Medicine, NCBI, has created all these databases, and almost any data I generate, I can just give to them and get a DOI for it, get a unique identifier for it, and it's saved in perpetuity. I think you folks probably in general are not so lucky, right? So finding some kind of third-party site that can store your data is incredibly important. There are things like Dryad. Here at the University of Washington, our libraries has recognized that being data librarians, managing data generated by researchers is actually really important. And so they offer a service called ResearchWorks where we can deposit our data in for free. We'll see how long it stays free. Dryad costs money. What's that? Oh, and Zenodo. Yeah. Thank you. The other thing that's really important is that your data is well documented itself. And I recently pulled down somebody else's data looking at bacteria in a water column, and they had said where in the water column they were pulling these things from, but they didn't say whether they were in metric units, whether they were in meters or centimeters or millimeters, and frankly that makes a huge difference to me, right? I care a lot whether I'm looking at a very shallow lake or a very deep lake. So having units of measurement be part of your metadata is super important. Oh, by the way, when you're naming variables, it's also great to put that unit of measurement in. There was a Mars Polar Climate Explorer that crashed into the planet. It made it all the way to Mars, crashed into the planet. I think it was like $500 million. I see hot nodding heads, right? The reason that happened is Lockheed's code that interfaced with some other code in there. One was using metric units, the other was using English units, right? So if they had said in the specification for how those two things were going to interact, right? If the variable names, if those kinds of things had referenced the units that were being used, might have not happened, right? Okay, so back to data though. The provenance of your data is really important. Getting a DOI for your data is really important. As Allison mentioned, Zenodo can help you do that. There are free resources out there that once you deposit the data somewhere can help you do that. And then again, treating your data as something that you would take to your department chair and say, promote me with this, that's a really important thing. All right, I've droned on for a really long time, but there's a lot more that I can talk to you about. These are some great web resources. We have our reproducibility working group here produce some guidelines that we give to all of our postdocs and grad students when they come in. But there's great stuff out there in the literature about other ways to make your data reproducible. So if we have time, I would like to open for a discussion, and I droned on for far too long. I'm sorry, but I'm really passionate about this, and I like to hear the sound of my voice, as I said. But I think a discussion here is really fun and useful, and so I kind of have some questions that maybe we can start the discussion. Is that I'm curious, who's tried to reproduce somebody else's experiment that involves computations? I see one. Okay, it's a bunch. Were you successful? Yeah. Yes? What's that? Not really, okay. Successful? Half successful, great. Successful? Sometimes, great. This is, wow, that's awesome. Fantastic. Please don't show this to NASA or NSF. I think that would be bad. So what's your sense? Was it a problem with the data? Was it a problem with the code? Was it a problem with the methods? Code? Methods. Data, do I have data? Anybody data? Just so we can have the trifecta. I had a data problem if that counts. So for those of you who have gone through this, did you contact the author? Were you ever able to absolutely resolve it, or did it stay an open issue?
Well, the author was a former student in my lab. So
Okay. Okay, anybody else?
For code-related stuff, you don't even get a response usually.
Okay, interesting. And I guess the code probably wasn't in GitHub, was it?
So most of the papers are in MATLAB. And if you try to replicate in another language, Python is my choice.
Yeah, I see.
And it usually never works out.
Side note, just to roll back a little bit, MATLAB has been particularly difficult for me because they change, and Mathematica too, every version changes things. And if you want to find an example where version changes can break stuff, just look at stuff done in MATLAB and Mathematica. So any other thoughts about how you resolve this or in your experiences? Has anybody tried to reproduce your stuff? Yeah, and?
I had one file that got corrupted, but after that.
Great, so come up here, put on the mic, and tell us what you did right. Oh, seriously, what do you think made that so successful?
It was just a little project.
Okay, so keeping things bite-sized, I guess, right? Anybody else? I have found that since I started keeping all of our lab's code in GitHub, the amount of the volume of email I get, like, can you send me this, can you send me this, has gone way down. And as we've improved our documentation there, that's decreased dramatically. And I don't know about the rest of you in the room, but I kind of am a busy fellow, and so I don't mind when I get fewer emails. It's generally a good thing. Anybody else? Yeah?
So that's a philosophical question. So reproducible does not mean correct.
That's absolutely right. So you could have the wrong scientific conclusion or the wrong scientific result, but it's reproducible. So we tend to think that if it's reproducible, it's absolutely right, but you make a really good point that I believe that reproducibility in open science is a step towards correctness, but it in itself does not actually mean that stuff is correct, right? If I have my algorithm for calculating the square root of something is dividing it by 2, it works fine for the number 4, but it doesn't work for a whole bunch of other stuff. But it's reproducible, right? I can reproducibly get the wrong answer. But the thing is, so this is why I come back to the idea that there are other aspects of reproducibility if we think about the terminology that I gave, right? There's that technical reproducibility, same result, or same data, same code, right? But then there's the other levels, right? So if I am concerned about your result, even though I can replicate it, or reproduce it, I should say, then you need to step up your game and re-implement that algorithm according to the method that was described. But then it's still possible that that algorithm, you implement it correctly, but the algorithm itself is completely wrong, right? It's just bogus that, you know, you're doing some statistical test that you shouldn't be doing or something like that. But if the code is available and the data are available and the methods are well written, then at least there's an opportunity for us as a community of like peers where we should be reviewing each other's work to hopefully identify that. But I think it's a really, really good point that just because it's reproducible or even replicable doesn't mean that it's accurate or that the conclusions you draw from it are accurate.
Yeah, I was just worried that, so if you make codes too easy to show, then that makes it easy for people not to write their analysis.
Yeah. Interesting. So by making everything plug and play, you take away the need of somebody to actually dig into it a little bit deeper. Yeah. You know, I'd never really thought much about that. I guess that's a really interesting point. I never really thought much about, you know, if you make things too low barrier to entry, then people can sort of misuse them. Yeah. Interesting. Any other comments on that? I'm curious to know what other people think about that. Do you think that's a real problem? Yeah, please.
Yeah, I see it all the time. People use like legacy code and stuff like that.
Mhm.
No idea how it works. It's just a black box. Goes in one way, comes out another, and that's people can use it for 30 years. It goes good.
Yeah.
I've gone through that type of code before, and I find like an error from 20 years ago.
Right. But I guess the point there is that you went through the code and you were able to find the error.
That's not all. That's usually not the case.
Yeah, that's usually not the case, right? So, you know, the less skilled individual who just plugs and chugs doesn't know and doesn't dig in, right? Doesn't even care, right? They just want the result for their paper, yeah.
That sounds like it's not really a question of whether or not we should share, but how we teach people to use software.
Great point. Great point. Yeah. I think, what do you think? It's probably the case that scientific software is not Excel. Or that came out weird, but that, you know, Microsoft's goal is to make the Office suite as easy to use as possible, right? And that's generally a good thing because we want our students to be able to write good papers and not to think about what they're doing in Word, but to think about what they're writing in Word, right? And I think maybe that's not the case for scientific software, right? That having it be plug and chug is good, but you have a responsibility as an educator or as the author of a piece of software to lay out whatever caveats are important, or, you know, to sort of describe the limitations of your tool and to be cognizant as you teach others to use it. You know, things like Geohack are an opportunity to do that, right? That you can have those discussions with people that might have only read your paper, but now you can actually say, oh, hey, wait, by the way, there's some of these other issues to go on. Great comments, I love it. Yeah.
I wonder,
Sorry.
I wonder if you could point to some of the resources that are out there, because I know this is something the Reproducibility Working Group has looked at about what should be the person who shares the responsibility of the person who shares their code versus the responsibility of the person adapting the code versus the responsibility of reviewers who are looking at that code.
I don't know if I have any specific resources. I can think about that, and we can certainly add them to the website. But it's an interesting question. So, you know, are there roles and responsibilities that are specific to a user and to the developer, and who was the third party?
Reviewers.
Oh, the reviewers. Yeah.
To look at your code.
Right.
And how you either adapted someone else's code or written your own code, et cetera.
Right. Oh, that's really interesting. Yeah, you know, I guess. So this is what a wonderful discussion from here, because this is really making me think hard about, again, communication. So now we're not necessarily talking about the quality of the code or the quality of the data, but it's about communicating, you know, how to use it and the limitations and things like that. And I'm thinking about a paper that we're writing right now. You know, have we made it clear that this is for 16S data and not 18S data, or something? That probably doesn't mean anything to most of you, but that there are certain limitations that we need to communicate and not just assume that our end users have. And again, this is about documentation, I think. Thank you. Yes?
So the papers that I have tried to replicate are usually applications of machine learning and deep learning.
Okay.
When you're trying to do that, it usually takes at least multiple days and sometimes multiple weeks to train a good model. So if somebody is trying to replicate that work, that amount of time is usually wasted. It's just running in the background. So when you have that just model object to share, it makes testing those results easier. For example, I was working on replicating satellite imagery-based crop production. It took me 2.5 months just to
train it, right? Yeah.
And that has no effect on how I understand the model or the methodology itself.
Yeah, so that's maybe a great thing that we could talk about a little bit, because I think many of us have things that are about long-running code, right? And it's hard to justify when, I don't know about you folks, but I don't have infinite computing resources. And so how do you justify reproducing somebody's result when you know it's going to take 2 months, right? And then you're not doing other science with that. And the NSF or DOE or whatever don't particularly want to give you the computer time to do that kind of work. It's a challenge, and I think we have a responsibility, if you like me share a passion about this, that we have to convince reviewers that they need to take the time to do that, and funding agencies and the supercomputing groups, the supercomputing operators, that there's value in reproducing other people's work, but it's hard. It's really hard to make that justification in your own environment with limited resources. Any thoughts on that? Is there something that we could do as a community that would would allocating, if we went to NERSC, for example, I don't know if there's any DOE users out there, but if we went to NERSC and said, you need to allocate 2% of your total cycles for replicating computational work, I wonder if they would get excited about that. Are there other ideas about things that we could do that convince funding agencies, convince groups that replication and reproducibility is valued? Yeah.
Sort of coming up with ways of randomly choosing small subsets to test on? Is that known? Or rather than reproducing
the entire study, right?
Say, I'm going to randomly test for 100 different.
So subsample and make sure that, I guess, so I like that idea, right? Because then you can scale down a problem to whatever resources you have available. I guess my only concern then, and this goes back to some of the other comments, is that then you can't talk about whether the conclusions drawn from the full study were valid, because you can't reproduce the whole study. But the nice thing about that, we always think about scaling up, but that you can actually scale down, right? You can make the fit, your laptop or whatever you have available. Other ideas, I love it. Yeah?
And that can be done only for the testing part.
Right.
For the training part.
That's right.
You'll need the full data.
The full 2 weeks and the full data set. Yeah. Yeah, I think again, if you feel passionate about this, in your community, instilling, making sure that there is value in reproducing other people's work, that we value that like we would value a publication. Well, is it the Journal of Open Source Software? Anybody familiar with this journal? Do they have a replication policy where they publish the primary paper, and then if you reproduce the work, you get that paper published as well? I think it's that journal, but it's a really neat idea, which you publish your paper, or you submit your paper to be published. The reviewers reproduce your work, and they get a publication for replicating the study. So obviously it's not as high as impact, but think about that. If you're the primary author on that first paper, you're like, this is great, because these folks just basically backed me up hardcore that my work is solid, right? And if you're that reviewer who put in all that time and energy, you got a publication out of it. Cool. So let's, I guess, thinking about maybe closing this up a little bit. I have 1 or 2 more questions. Is there anybody in this room who has already taken specific actions for making sure that their work was more reproducible? Yeah.
So I use a snake or make files to automate.
Cool.
So just go in there, type snake make everything else.
Can you let other folks know what make is and how that works?
So make is how typically people manage the problem with big code base, change one C file, and rerun the whole compilation process. So So you can, it's the same problem as if you're changing one of the inputs of your data analysis. So you can use Beck to manage your data analysis pipelines. Sort of, it's, and you could say if you leave one step, you know, just to rerun that step. And then SnakeMake is a sort of more convenient version written in Python for scientific purposes.
That's cool. Thank you for. I know Make and we use Make, but I've never used SnakeMake. That's a new one to me. Anybody using workflow managers, like Taverna or Galaxy or no? So that's an option, a lot like he said, but they tend to be a little bit lower free energy barrier to get into. Are workflow managers, and so in these things you take pieces and you plug them together and you say this is the workflow, right? And many times it can actually be graphical. Galaxy's pretty cool. It was made originally for omics data analysis, but you can put anything you want between a Galaxy entity. And imagine that your script takes certain inputs and then produces certain outputs. You describe that to Galaxy, and now you can start to plug pieces together where this output goes into this input and that output comes into this input. So workflow managers are really great if you have complex workflows that you run repeatedly. Anybody else? All right, so I have one final question for everybody. When you go back home, what are you going to remember? What actions do you think you'll take towards making your work more reproducible based on everything you've learned here? Yeah, I love it. You get a prize. I'll give you $5 later. You use version control, right? That's probably the lowest, again, I keep saying lowest free energy barrier because, you know, I'm a chemist or whatever, but the lowest free energy barrier to get your stuff more reproducible. Anything else? Other things? Maybe Docker, maybe look into Docker. Did you do AWS as part of this? Yeah, maybe use AWS, right? Any other things?
Open data.
Open data. Yeah, great.
I was going to say make environments for actual version writing.
Yeah. That's actually, virtual environments are a lighter weight version of things like AWS and Docker. So if virtual environments are a good thing to familiarize you with. Were you going to raise your hand or something? Oh, okay. Anybody else? Well, it's been a lot of fun, and I learned a ton of new stuff, and now I actually have to add new slides to this. So this was really great. I really appreciate the involvement in the discussion. Thanks, everybody.